Chapter 1 of History of Chemistry, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. History of Chemistry, Volume 2, by Sir Edward Thorp. Chapter 1. State of Chemistry in the Middle of the 19th Century. In the preceding volume, an attempt was made to outline the significant features in the development of chemistry, as an art and as a science, from the earliest times down to about the middle of the last century. Since that time, chemistry has progressed at a rate and to an extent unparalleled at any period of its history. Not only have the number and variety of chemical products, inorganic and organic, been enormously increased, but the study of their modes of origin, properties, and relations has greatly extended our means of gaining an insight into the internal structure and constitution of bodies. This extraordinary development has carried the science beyond the limits of its own special field of inquiry, and has influenced every department of natural knowledge. Concurrently, there has been a no less striking extension of its applications to the prosperity and material welfare of mankind. With the death of Davy, the era of brilliant discovery in chemistry, wrote Edward Turner, appeared for the moment to have terminated. Although the number of workers in the science steadily increased, the output of chemical literature in England actually diminished for some years. And as regards inorganic chemistry, few first-rate discoveries were made during the 2 decades prior to 1850. Chemists seemed to be of Turner's opinion that the time had arrived for reviewing their stock of information, and for submitting the principal facts and fundamental doctrines to the severest scrutiny. Their activity was employed not so much in searching for new compounds or new elements, as in examining those already discovered. The foundations of the atomic theory were being securely laid. The ratios in which the elements of known compounds are united were being more exactly ascertained. The efforts of workers, Graham excepted, seemed to be spent more on points of detail, on the filling in of little gaps in the chemical structure as it then existed, than in attempts at new developments. For a time, during the early 30s, chemists struggled with the claims of rival methods of notation, and it was only gradually that the system of Berzelius gained general acceptance. At none of the British universities was there anything in the nature of practical tuition in chemistry. Thomson, at Glasgow, occasionally permitted a student to work under him, but no systematic instruction was ever attempted. The first impulses came from Graham in 1837, when he took charge of the chemical teaching at the University of London, and when, in 1841, he assisted to create the Chemical Society of London. 4 years later, the Royal College of Chemistry in London was founded, and placed under the direction of August Wilhelm Hofmann, one of the most distinguished pupils of Liebig. Under his inspiration, the study of practical chemistry made extraordinary progress, and discovery succeeded discovery in rapid succession. In bringing Hofmann to England, we had, in fact, imported something of the spirit and power of his master Liebig. Among the pupils and co-workers of Hofmann were Warren de la Rue, Abel, Nicholson, Mansfield, Medlock, Crookes, Church, Gries, Martius, Sell, Divers, and Perkin. Whilst at Gießen, he had begun the study of the organic bases in coal tar, with a view more especially of establishing the identity of Fritz's aniline with the benzodime of Xenon and the crystalline of Unverdorben. Hofmann continued to cultivate with unremitting zeal the field thus entered. With Musprat he discovered paratoluidine and nitranilin, with Cahors allyl alcohol. His pupil Mansfield worked out, at the cost of his life, the methods for technical extraction of benzene and toluene from coal tar, and thereby made the coal tar color industry possible. It was in attempting to synthesize quinine by the oxidation of aniline that Perkin, then an assistant at the college, obtained in 1856 aniline purple or mauve, as it came to be called by the French, the first of the so-called coal tar coloring matters. In 1859 this was followed by the discovery of magenta or fuchsine by Verkine. For its manufacture, Medlock, one of Hofmann's pupils, in 1860 devised a process by which, for a time, it was almost exclusively made. Hofmann studied the products thus obtained, and showed that they were derivatives of a base he called rose aniline, and he demonstrated that the coloring matters were only produced through the concurrent presence of aniline and toluidine. He also proved that the base of the dye known as aniline blue was triphenyl rosaniline. As the result of these inquiries, he obtained the violet or purple coloring matters known by his name. Lastly, all his classical work on the amines, ammonium compounds, and the analogous phosphorus derivatives was done at the Royal College of Chemistry. Prior to the establishment by Liebig in 1826 of the Gießen laboratory, the state of chemistry in Germany was not much, if at all, better than with us. The creation of the Gießen school initiated a movement which has culminated in the preeminent position which Germany now occupies in the chemical world. Students from every civilized country came to study and to work under its leader, and to carry away with them the influence of his example, the inspiration of his genius, and the stimulating power of his enthusiasm. Justus von Liebig was born at Darmstadt on May 12, 1803, and after graduating at Erlangen, where he worked on the fulminates, he repaired to Paris and entered the laboratory of Gay-Lussac, with whom he continued his inquiries. Returning to Germany, he was appointed professor of chemistry at Gießen in 1826, and began those remarkable series of scientific contributions upon which the superstructure of organic chemistry largely rests. He investigated the cyanates, cyanides, ferrocyanides, thiocyanates, and their derivatives. In conjunction with Wohler, he discovered the group of the benzoic compounds and created the radical theory. With Wohler also he investigated uric acid and its derivatives. He discovered hippuric acid, fulminuric acid, chloral, chloroform, aldehyde, thialdine, benzyl, and elucidated the constitution of the organic acids and the amides. He greatly improved the methods of organic analysis and was thereby enabled to determine the empirical formulae of a number of carbon compounds of which the composition was imperfectly known. He practically laid the foundations of modern agricultural chemistry, and to his teaching is due the establishment of an important branch of technology, the manufacture of chemical fertilizers. He worked on physiological chemistry, especially on the elaboration of fat, on the nature of blood, bile, and on the juice of flesh. He studied the processes of fermentation and of the decay of organized matter. He was a most prolific writer. The Royal Society's catalogue of scientific papers enumerates no fewer than 317 contributions from his pen. He was the founder of the Annalen der Chemie, which is now associated with his name, and of the Jahresbericht. He published an encyclopedia of pure and applied chemistry and a handbook of organic chemistry. His Familiar Letters on Chemistry was translated into every modern language and exercised a powerful influence in developing popular appreciation of the value and utility of science. Liebig left Gießen in 1852 to become professor of chemistry at the University of Munich and president of the Academy of Sciences. He died at Munich on April 18, 1874. With the name of Liebig, that of Wohler is indissolubly connected. Although the greater part of their work was not published in conjunction, what they did together exercised a profound influence on the development of chemical theory. Friedrich Wohler was born at Eskersheim, near Frankfurt, on July 31, 1800. After studying at Marburg, where he discovered, independently of Davy, cyanogen iodide, and worked on mercuric thiocyanate, he went to Heidelberg and investigated cyanic acid and its compounds under the direction of Gmelin. In 1823 he worked with Berzelius at Stockholm, where he prepared some new tungsten compounds and practiced mineral analysis. In 1825 he became a teacher of chemistry in the Berlin Trade School. Here he succeeded for the first time in preparing the metal aluminium and in effecting the synthesis of urea, one of the first organic compounds to be prepared from inorganic materials. Jointly with Liebig, he worked upon mellitic and cyanic and cyanuric acids. In 1832, Wohler, now appointed to the Polytechnic at Cassel, began with Liebig their memorable investigation on bitter almond oil. In 1836 he was called to the chair of chemistry in the University of Göttingen, and with Liebig attacked the constitution of uric acid and its derivatives, the last great investigation the friends did in common. Wohler subsequently devoted himself mainly to inorganic chemistry. He isolated crystalline boron, and prepared its nitrides, discovered the spontaneously inflammable silicon hydride, titanium nitride, and analyzed great numbers of minerals and meteorites and compounds of the rarer metals. He made Göttingen famous as a school of chemistry. At the time of the 120th year of his connection with the university, it was found that upwards of 8,000 students had listened to his lectures or worked in his laboratory. He died on September 23, 1882. In France, Dumas exercised a no less powerful influence. If Liebig could reckon among his pupils Rettenbacher, Bromies, Varentrop, Gregory, Playfair, Williamson, Gilbert, Brodie, Anderson, Gladstone, Hoffmann, Will, and Fresenius, Dumas would point to Boulay, Peria, Stas, Melsons, Wurtz, and Leblanc, all of whom did yeoman service in developing the rapidly expanding branch of organic chemistry. Jean-Baptiste André Dumas was born on July 14, 1800, at Alais, where he was apprenticed to an apothecary. In his 16th year he went to Geneva and entered the pharmaceutical laboratory of Lavoisier. Without apparently having received any systematic instruction in chemistry, he commenced the work of investigation. With Condé, he established the therapeutic value of iodine in the treatment of goitre. With Prévost, he attempted to isolate the active principle of digitalis and studied the chemical changes in the development of the chick in the egg. In his 24th year, Dumas went to Paris and became répétiteur de chimie at the École Polytechnique. He joined Audouin and Brongniart in founding the Annales des Sciences Naturelles, and began his great work on chemistry applied to the arts, of which the first volume appeared in 1828. At about this time he devised his method of determining vapor densities, and published the results of a number of estimations made by means of it. With Boulay he began an inquiry on the compound ethers, out of which grew the etherin theory, which served as a stepping stone to the theory of compound radicals, subsequently elaborated by Liebig and Wohler. Dumas discovered the nature of oxamide and of ethyl oxamate, isolated methyl alcohol, and established the generic connection of groups of similarly constituted organic substances, or, in a word, the doctrine of homology. His work on the metaleptic action of chlorine upon organic substances eventually effected the overthrow of the electrochemical theory of Berzelius, and led to the theory of types, which, in the hands of Williamson, Laurent, Gerhardt, and Odling, was of great service in explaining the analogies and relationships of whole groups of organic compounds. He worked in every field of chemistry. He invented many analytical processes, established the gravimetric composition of water and of air, and revised the atomic weights of the greater number of the elements then known. Dumas exercised great influence in scientific and academic circles in France. He was an admirable speaker, and had rare literary gifts. On the creation of the Empire he was made a senator, and was elected a member of the Municipal Council of Paris, of which he became president in 1859. He died on April 11, 1884. It was largely through the influence of these master minds that chemistry took a new departure. Prior to their time, organic chemistry hardly existed as a branch of science. Organic products, as a rule, were interesting only to the pharmacist, mainly by reason of their technical or medicinal importance. But by the middle of the 19th century, the richness of this hitherto untilled field became manifest, and scores of workers hastened to sow and to reap in it. The most striking feature indeed of the history of chemistry during the past 60 years has been the extraordinary expansion of the organic section of the science. The chemical literature relating to the compounds of carbon now exceeds in volume that devoted to all the rest of the elements. In the middle of the 19th century, chemists began to concern themselves with the systematization of the results of the study of organic compounds, and something like a theory of organic chemistry gradually took shape. From this period we may date the attempts at expressing the internal nature, constitution, and relations of substances which, step by step, have culminated in our present representations of the structure and spatial arrangement of molecules. In 1850, the dualistic conceptions of Berzelius ceased to influence the doctrines of organic chemistry. The enunciation by Dumas of the principle of substitution, and its logical outcome in the nucleus theory and in the theory of types, had not only effected the overthrow of dualism, but was undermining the position of the radical theory of Liebig and Wohler. The teaching of Gerhardt and Laurent had spread over Europe and was influencing those younger chemists who, while renouncing dualism, were not wholly satisfied with a belief in compound radicals. Williamson's discovery in 1850 of the true nature of ether and of its relation to alcohol, and his subsequent preparation of mixed ethers, served not only to reconcile conflicting interpretations of the process of etherification, but also to reconcile the theory of types with that of radicals. Lastly, his method of representing the constitution of the ethers and their mode of origin gave a powerful stimulus to the use of type formulae in expressing the nature and relations of organic compounds. Other representative men of the middle period of the 19th century, in addition to Williamson, were Graham and Bunsen. The three men were investigators of very different type, and their work had little in common, but each was identified with discoveries of a fundamental character, constituting turning points in the history of chemical progress, valuable either as regards their bearing on chemical doctrine or as regards their influence on operative chemistry. Thomas Graham was born in Glasgow on December 21, 1805, and after studying under Thomas Thomson at the University of that city, attended the lectures of Hope and Leslie in Edinburgh. In 1830 he succeeded Urey as teacher of chemistry at Anderson's College in Glasgow, and in 1837 was called to the chair of chemistry in the newly founded University of London in succession to Edward Turner. In 1854 he was made Master of the Mint. He died in London on September 16, 1869. Graham's work was mainly devoted to that section of the science now known as physical chemistry. His contributions to pure chemistry are few in number. By far the most important is his discovery of metaphosphoric acid and its relations to the other modifications of phosphoric acid. Ortho, or ordinary phosphoric acid, was known to Boyle. Pyrophosphoric acid was discovered by Clark. Graham's work is noteworthy as first definitely indicating the inherent properties of the acids to combine with variable but definite amounts of basic substances by successive replacement of hydroxyl groups, the property we now term basicity, and was of fundamental importance in regard to its bearing on the constitution of acids and salts. Graham's fame chiefly rests upon his discovery of the law of gaseous diffusion, 1829 to 1831, upon his work on the diffusion of liquids, and upon his recognition of the condensed form of hydrogen he termed hydrogenium. Questions involving the conception of molecular mobility, indeed, constituted the main feature of his inquiries. We owe to him, among others, the terms crystalloid, colloid, dialysis, atmolysis, occlusion, all of which have taken a permanent place in the terminology of science. Alexander William Williamson was born at Wandsworth, London, on May 1, 1824. His father, a Scotchman and a fellow clerk of James Mill, the father of John Stuart Mill, in the East India House, took an active share in the foundation, in 1826, of the University of London, subsequently known as University College. In 1840 the younger Williamson entered the University of Heidelberg with the intention of studying medicine, but under the influence of Leopold Gmelin he turned to chemistry. In 1844 he went to Gießen to work under Liebig, and there made his first contributions to chemical science, namely, on the decomposition of oxides and salts by chlorine, on ozone, and on the blue compounds of cyanogen and iron. After graduating at Gießen, he went in 1846 to Paris, where he came under the influence of Comte, with whom he studied mathematics. In 1850, at Graham's solicitation, he was appointed to the chair of practical chemistry at University College, vacant by the death of Founds. He at once embarked upon those researches which constitute his main contribution to science. In the attempt to build up the homologous series of the aliphatic alcohols from ordinary alcohol, he succeeded in demonstrating the real nature of ether and its genetic relation to alcohol, and in explaining the process of etherification. The memoirs, 1850–52, in which he embodied the facts, had an immediate influence on the development of chemical theory. His explanation of the process of etherification familiarized chemists with the idea of the essentially dynamic nature of chemical change. He imported the conception of molecular mobility not only into the explanation of such metathetical reactions as the formation of the ethers, but into the interpretation of the phenomena of chemical change in general. In these papers, as also in one on the constitution of salts published in 1851, he attempted to systematize the representation of the constitution and relations of oxidized substances, organic and inorganic, by showing how they may be regarded as built up upon the type of water considered as hydrogen, oxygen, hydrogen, or HOH, in which the hydrogen atoms are replaced, wholly or in part, by other chemically equivalent atoms. This idea was immediately adopted by Gerhardt, was further elaborated by Odling and Kekule, and was eventually developed into a theory of chemistry. Williamson continued to direct the laboratory of University College until 1887, when he retired to the country. He died at Hindhead on May 6, 1904. Robert Wilhelm Bunsen was born at Göttingen on March 31, 1811, and after studying chemistry under Stromeyer, the discoverer of cadmium, went to Paris and worked with Gay-Lussac. In 1836 he succeeded Wohler as teacher of chemistry in the Polytechnic School of Cassel, and in 1842 became professor of chemistry in the University of Marburg. In 1852 he was called to Heidelberg, and occupied the chair of chemistry there until his retirement in 1889. He died at Heidelberg on August 16, 1899. Bunsen first distinguished himself by his classical work on the cacodyl compounds obtained as the result of an inquiry into the nature of the so-called fuming liquor of cadet, an evil-smelling, highly poisonous, inflammable liquid formed by heating arsenious oxide with an alkaline acetate. The investigation, 1837 to 1845, is noteworthy, not only for the skill it exhibits in dealing with a difficult and highly dangerous manipulative problem, but also for the remarkable nature of its results, and on account of their influence on contemporary chemical theory. The research, in the words of Berzelius, was the foundation stone of the theory of compound radicals. The name cacodyl or cacodyl was suggested by Berzelius in allusion to the nauseous smell of the compounds of the new radical arsine dimethyl, AsCH32, as it was subsequently termed by Kolbe. Bunsen greatly improved the methods of gasometric analysis. These he applied in conjunction with Playfair to an examination of the gaseous products of the blast furnace in the manufacture of iron, and thereby demonstrated the enormous waste of energy occasioned by allowing the gases to escape unused into the air, as was then the universal practice. This inquiry effected a revolution in the manufacture of iron as important, indeed, as that due to the introduction of the hot blast. Bunsen devised methods for determining the solubility of gases in liquids, for ascertaining the specific gravity of gases, their rates of diffusion, and of combination or inflammation. In 1841 he invented the carbon-zinc battery and applied it to the electrolytic production of metals, notably of magnesium, the properties of which he first accurately described. In 1844 he contrived the grease-spot photometer, which was long in general use for ascertaining the photometric value of illuminating gas. His methods of ascertaining the specific heats of solids and liquids were simple, ingenious, and accurate. In 1855 through 1863 he carried out, in conjunction with Roscoe, a long series of investigations on the chemical action of light. In 1859, in association with Kirchhoff, he devised the first methods of spectrum analysis, and explained the origin and significance of the Fraunhofer lines in the solar spectrum, thus laying the foundations of solar and stellar chemistry. The application of the spectroscope to analytical chemistry almost immediately resulted in his discovery of cesium and rubidium. Bunsen worked on problems of chemical geology, and made a long series of analyses of volcanic products. With Shishkov he examined in 1857 the products of fired gunpowder. He effected many improvements in analytical chemistry, devised the iodometric method of volumetric analysis, and systematized the processes of water analysis. Lastly, he invented the gas burner, a piece of apparatus with which his name is inseparably associated, and which has been of inestimable service to operative chemistry and in the arts. Bunsen was no theorist, and purely speculative questions had little or no interest for him. At the same time, he was a great teacher, and made the chemical school of Heidelberg no less famous than the schools of Gießen and Göttingen. The mass of material relating to the development of chemistry which has been accumulated during the past 60 years is so vast that it would be hopeless to attempt to survey it in detail within the limits of such a work as this. Nor, indeed, is this required in a history of this character. Those who desire information concerning the origin and sequence of the facts which collectively make up the superstructure of modern chemistry must be referred to the encyclopedias or larger treatises, or preferably to the numerous monographs dealing with special sections, which the volume and complexity of the matter to be dealt with seem to render increasingly necessary. All we can do here is to attempt to show what has been the main outcome of this 60 years of incessant effort to elucidate the mysteries of chemical phenomena and to ascertain the nature of the conditions which control, modify, or determine them. All this effort is ultimately directed to the solution of the fundamental problem of the constitution of matter. The most significant result of this endeavor has been the elaboration and consolidation of the doctrine of chemical atoms, not necessarily of atoms in the limited Daltonian sense, but of atoms considered as associations of particles, or corpuscles, that is, of entities which may be divisible, but which in the main are not divided in the vast number of the transformations in which they are concerned. This modification of the original conception of Dalton has been thought by some to destroy the basis upon which his theory really rests. There is no necessity for such an assumption. So pronounced an atomist as Graham, as far back as 1863, in a suggestive paper entitled Speculative Ideas on the Constitution of Matter, enlarged the conception of the Daltonian atom in precisely the sense which recent experimental work appears to require. The present position, too, as it affects chemists, was equally well stated by Kekule in 1867 in the following terms. The question whether atoms exist or not has but little significance from a chemical point. Its discussion belongs rather to metaphysics. In chemistry, we have only to decide whether the assumption of atoms is an hypothesis adapted to the explanation of chemical phenomena. More especially have we to consider the question whether a further development of the atomic hypothesis promises to advance our knowledge of the mechanism of chemical phenomena. I have no hesitation in saying that, from a philosophical point of view, I do not believe in the actual existence of atoms, taking the word in its literal significance, of indivisible particles of matter. I rather expect that we shall some day find for what we now call atoms a mathematico-mechanical explanation which will render an account of atomic weight, of atomicity, and of numerous other properties of the so-called atoms. As a chemist, however, I regard the assumption of atoms not only as advisable, but as absolutely necessary in chemistry. I will even go further and declare my belief that chemical atoms exist, provided the term be understood to denote those particles of matter which undergo no further division in chemical metamorphoses. Should the progress of science lead to a theory of the constitution of chemical atoms, important as such a knowledge might be for the general philosophy of matter, it would make but little alteration in chemistry itself. The chemical atoms will always remain the chemical unit, and for the specially chemical considerations we may always start from the constitution of atoms, and avail ourselves of the simplified expression thus obtained, that is to say, of the atomic hypothesis. We may, in fact, adopt the view of Dumas and of Faraday, that whether matter be atomic or not, thus much is certain, that granting it to be atomic, it would appear as it does now. The greater part of that which follows will be devoted, therefore, to an exposition of certain of the great advances in knowledge, many of them of primary importance, which have been made during the last 50 or 60 years, and which have served to strengthen this extended conception of the atomic theory, and to establish its position as an article of the scientific faith of the 20th century. End of Chapter 1.